Welcome to qnawire.
Here we're given the observed wavelength in an experiment in which we're going to have the electronic transition from n6 to n equal 2 on the hydrogen atom. So in this case, in order to do the calculations, remember that the energy of the photon is going to be equal to h nu, and it's going to correspond to the difference, in this case, of the energy at n6 minus the energy at n1. Sorry, over here, the other way around. The energy at n1 minus the energy at n6, which is the final and the initial states, respectively. This equation, we can transform it a little bit, remembering that h times nu, we can relate nu with lambda, as the frequency is going to be equal to c divided by lambda. So over here we can relate this as hc over lambda, for which we are going to find the Rydberg equation, which tells us that 1 over lambda is going to be equal to the Rydberg constant times z squared multiplied by 1 over the final state squared minus 1 over the initial state squared. The value for the Rydberg constant for hydrogen is going to be equal to 1.0967758 times 10 to the 7 meters to the minus 1. In this case, what corresponds to the theoretical value would be, since the atomic number for hydrogen is equal to 1, we're going to have our Rydberg constant, 967758, times 10 to the 7 meters to the minus 1, multiplied by 1 over the final state, which is going to be n equal 1, minus the initial state, which is going to be 6. Oh, sorry, over here I misread. The final state is n equal 2, not n equal 1, so it should be over here 2 squared. Sorry about that. So with this, our result gives us 913,979.833 meters to the minus 1, which upon taking the inverse, we're going to get that the value for lambda gives us this result, which upon inversion gives us 4.103 times 10 to the minus 7 meters, which is equal to 410.3 nanometers. So this would be our theoretical value for lambda in this scenario. And as you can see, the theoretical value is going to match up perfectly with the observed wavelength in your experiment.